A Bernoulli trial consists of two events whose probabilities sum to 1. Let's take two examples. A coin is thrown. The events H, which means getting heads, and T, which means getting tails, have probabilities that sum to 1. That is, the probability of event H plus the probability of event T equals 1. Notice here that I didn't say anything about the coin being unbiased. The coin does not necessarily have to be unbiased. The probability of heads could be 1/3. We could have a loaded coin. But we are assuming that the probability of tails will be 2/3. Because for Bernoulli trial, that is a single throw of this coin, these probabilities must sum to 1. An unbiased die is thrown. The events getting a 6 and not getting a 6 have probabilities that sum to 1. So that means that we have this equation here. Well, for an unbiased die, the probability of getting a 6 is 1/6. The probability of not getting a 6 is 5/6. There are 6 outcomes when we throw a die. And for an unbiased die, those 6 outcomes are equally likely. So the event not getting a 6 has 5 elements. So we put the number of elements in that event or set over the total number of outcomes, which is 6. For the case of throwing an unbiased die, there are many events that we could consider. We could consider the event getting an even number. And we know that the probability of this event is a half. It's 3/6. There are 3 even numbers. We could also consider this event. This is the event of getting a 5. The probability of getting a 5 is 1/6. But you see, if we add these probabilities, half plus 1/6 is 4/6, which is not equal to 1. So these two events, getting an even number and getting a 5 on a single throw of an unbiased die, do not constitute a Bernoulli trial. Now let's consider an unbiased coin that is thrown 3 times. So each trial or throw is a Bernoulli trial if we consider the events getting heads or getting tails. Those events have probabilities that sum to 1. And the 3 trials or throws are identical. So the probabilities don't change from trial to trial or throw to throw. We are going to make up a probability distribution table for the number of heads that appear in 3 throws of this coin. In a previous video, we discussed the sample space for the outcomes of 3 throws of a fair coin. So we've already answered some of these questions. But this example leads us into the binomial distribution, so we're going to go through it in detail in this video and in the next video. So we want the probability of getting 0 heads. Well, that's just the same thing as the probability of getting 3 tails, which we know is 1/8. Only one outcome in the sample space involves 3 tails, so it's just 1 out of 8 outcomes, equally likely outcomes. Now we want the probability of getting 1 head. I'll just write 1H for this. So we look at the set of outcomes that consist of just 1 head. We look at that set and we count the elements in it. And we've done this before. This set consists of outcomes that have just 1 head, so we can call this event or set 1H. Its probability is the number of elements in it, which is 3/8, the total number of elements. By the way, I could call the probability of getting 3 tails the probability of 0 heads. Next we want the probability of 2 heads. Well, the event 2H consists of 3 outcomes, HHT, HTH, and THH. So we've 3 elements in that event, so we've 3 over 8. And finally, we want the probability of getting 3 heads. Well, there's only one outcome that consists of 3 heads, so that answer is 1/8. Here is a probability distribution table for the number of heads showing in 3 throws of a fair coin. If a coin is thrown 3 times, well, it has to show either 0 or 1 or 2 or 3 heads. So the probabilities must sum to 1. That's true for any probability distribution table. It's a certainty that 0, 1, 2 or 3 heads will show. The number of heads is said to follow a binomial distribution. Now in the next video we will look at this example in more detail and show how to calculate these probabilities by using a formula.